pleasure to have Volodymyr. Excuse me. Yes, to have Volodymyr here. Most of you know him because he visits every other week usually, and so he agreed to give us a seminar on fluctuation probes of QCD matter and heavy ion conditions. So please take it on.
Yeah, so thank you so much. So it's a great pleasure to be here. I think even though I was a postdoc here, it's actually my first HIT seminar.
Is that right?
There were a couple of NT seminars, but I believe it is the first HIT seminar.
All
so
right.
Great to finally give it here. And I will talk about a couple of topics related to fluctuation probes of QCD matter in heavy ion collisions, and work done in collaboration with Volker here, with Adam's DAC in Poland, and of course with collaborators in Houston. So a couple of undergrad, Jonathan Para, a graduate student, Volodymyr Kuznetsov, a postdoc, Roman Poberezhnyuk, and a fellow faculty, Claudia Roy. So there is quite some collaborative activity here going on. So introduction here, which I think is an old question, but still very much relevant, is the phase structure of QCD, where we know actually not that much, not that many things which are set in stone. So we know about properties of cold nuclear matter, about dense nuclear matter, especially with the neutron star observation in recent years. We also know from first principles, as far as theory goes, a crossover transition between hadronic matter and protonic matter to the critical temperature of roughly 155 MeV. And using extrapolations from lattice, we also have an idea how this transition changes as we go to non-zero baryon density, but we can only extrapolate so far from zero chemical potential. We had a nice talk earlier today about the sign problem, which doesn't allow us to directly compute the stuff here.
So what's the temperature for nuclear liquid gas?
This one around 15 to 20 MeV. Yeah.
So I mean, the famous results from LIGO and undergraduate.
Yeah.
So when can we actually start putting numbers on the neutron star, kind of the high mu axis?
Okay. So well, we're already putting numbers there. We are putting numbers in a particular direction of isospin asymmetry. One has to also acknowledge that there is no liquid gas transition, for example, for a high isospin asymmetry. So I think with LIGO measurements and modeling of merger, there will be more constraints on finite temperature part of cold and dense matter. So I think that we will start putting numbers in the coming years there as well. But actually, this is what we want eventually, get something like this, in the sense that we have some numbers and phase transitions quantified, and to know where critical point is, if it does exist in the first place, and then how the transition line looks like, and so on and so forth. Heavy ion collisions is, of course, one of the primary methods accessible to access finite density matter, but which is also at finite temperature, not at zero temperature. And one of the key questions here, maybe the first one to answer, is whether there is critical point, and if it does, where exactly is it located? So this is still open question. There have been new developments which gives us hints where it might be. So I will cover these developments here based on these two recent preprints. So if there is a phase transition, what one expects is to have a first order, a mixed phase of a first order phase transition where, well, essentially it's where thermodynamic potential becomes a multi-valued function. So it's not anymore a one-to-one correspondence between a pair of T and mu values and say thermodynamic potential. So we, of course, know famous examples from textbooks of liquid gas transition and the Maxwell loops. Usually this is pressure versus density isotherms. So here actually it makes sense to work in a slightly different variables. So let's say we are at zero chemical potential. We can probe the, of course, the temperature axis, And since there is no phase transition, the entropy density is just a monotonically increasing function of the temperature. However, if we had a phase transition at zero chemical potential, maybe not in QCD, but in some model or theory, simplified theory, you would normally obtain something like an S-shaped form of the entropy density. So it's simply reflects the fact that it is multi-valued function, and in equilibrium, of course, you have a jump. Since there is more than just equilibrium, but also metastable and unstable phases, you can have also a more complete structure as this non-monotonic behavior. So this how a phase transition would look like at constant chemical potential as you cross the mixed phase region. And if indeed this happens at finite mu, because there is a, say, critical point, then we would expect in T mu plane something like this. So you have here lines of constant entropy density, and these lines would start crossing in the region of the mixed phase, right? Because in the region of mixed phase, entropy density would be a multi-valued function. So there can be more than one value of entropy density. These are what these different dashed dotted lines represent, which cross at the same point in T and mu diagram. So more specifically, you could define the location of critical point where these crossings appear for the first time. So this one can rewrite in terms of derivative of temperature with respect to entropy at constant chemical potentials. Again, this is in complete analogy to this liquid gas transition where you have pressure versus density isotherms. So here we have instead constant chemical potential values. And so, so one strategy here would be to start here where we have lattice data and see if there are indications that lines of constant entropy density cross. Of course, we don't have lattice simulations directly here at positive mu b, so we have to extrapolate. And this plot shows lines of constant entropy density computed at imaginary values of chemical potential, because at imaginary values there is no sign problem. And if you, and so what's plotted here are lines of constant entropy density versus mu b squared, and by eye it looks pretty linear to me, right? So what this motivates us to do is to consider the following extrapolation by expanding temperature as function of chemical potential corresponding to a fixed value of entropy density. So you can define an expansion, and the coefficients are particular derivatives holding entropy constant. So there are some technical details involved in this, which I will not go through. And to leading order, you would have parabolic lines of constant entropy density. So this is explicit expression for the expansion coefficient, which you can express in terms of entropy density, its temperature derivative, as well as baryon number susceptibility. So these are all at mu b equals 0. So this one can take as input from lattice. So this is something we did. So we computed this coefficient, plugged it into this our approximation of line of constant entropy, and then we built the behavior of entropy at finite mu b. So we first start at small values of mu b over t, because at small mu b over t we can compare the results to available constraints from lattice QCD. So this is mu b over t of 1 up to 3.5. The solid line is the average value. A bunch of these semi-transparent lines is error propagation. So we sample a propagation of lattice error bars to have an idea how far we can go. So we have excellent agreement with available constraints at small mu b over t, and if we continue going to higher mu b, what we observe is then that these lines of entropy normalized here by the temperature at constant mu b, it develops this structure where it can have, well, the S shape that I discussed previously. So you have here temperature, that would be a vertical line, and the whole and the whole line here is the constant mu value. So you can see that there is, for instance, here 1, 2, 3 different values of entropy, which correspond to the same temperature, same chemical potential. So this is the emergence of emergence of the multivalued behavior, which is consistent with what we expect for a first order phase transition.
So this is only 2 mu b squared.
It is only 2 mu b squared.
If you go to higher mu b power
Yeah,
squared,
so for higher mu b's, for higher coefficient, you will have high order temperature derivatives and high order susceptibilities, which are not as well constrained. We have considered what happens with high order. So we see this structure still emerges, but there could be some movement which we didn't estimate error, because we have to take into account errors of high order susceptibilities and high order temperature derivatives. So this is under investigation.
I mean, how good is this approximation? As you're talking, just kind of comparing the units in your upper right. So the temperature, T naught is, a couple hundred MeV, and the mu's you have there are many hundreds of MeV.
Yeah.
So, but so alpha has some unit.
So alpha is MeV to the minus first. Yes.
Okay.
It's
So
not plotted here, but it is.
what's typically the relative magnitude of the second term?
Oh, okay. The second.
How convergent is it?
Oh, okay. So the magnitude. So let's see. So we have. So we start, let's say, at 150 MeV, and we get here where critical point is to 110 MeV. So it is 30, 40 MeV when we reach the critical point in this expansion.
Sorry, so again, T naught is.
T naught is so we start at mu equals 0. Let me go back 1 second. So we start here. So this is, for instance, T naught. And then we go to finite mu, temperature decreases. So we go, so T naught, which corresponds to critical point, is 140 in our calculation. And we get to 110. So this gives you an...
That's a correction.
Well, that's a correction, right? So leading order, it would be just flat line, right? So that is the correction. Well, that is how it changes with mu b to leading order.
I think just to come back to the question of the convergence of this expansion.
Yeah.
Do you have an estimate of the next term?
We had an estimate of the next term, but we didn't have an estimate of the error of the next term. Yeah. So we don't know how convergent it is at the moment, right? So we present it as a proof of principle that if we could reliably estimate these lines, either via expansion, which is motivated by the behavior at my imaginary mu, or by some other means, maybe in the future we will get lattice data at small mu b directly if new methods emerge, or maybe we can combine finite imaginary mu data directly as well. So this, hopefully we will be able to do more precise estimation of the contours, but the method will remain the same. You look for where the contours cross. So you want to solve these equations, and then you have to analyze whether you find the solution and your estimation of contours is still accurate there, and then you can make stronger conclusions than the proof of principle presented here. Yes.
I mean, for me, this structure is zero by construction.
What should be zero?
I mean, this should be zero by a model construction.
This should be zero.
This should be zero. It should have this structure.
It should have the structure. Okay, because if they cross, they give you the structure. That's okay. So well, they cross, but do we know a priori that it's 3 solutions as we expect or more? So that we didn't know a priori. So I think there is a little bit more than by construction. But it's also a fair question how accurate it is once we reach that point. Okay, but if we trust it, at least for a second, and we just restrict ourselves to mu b square term, and we propagate the errors from the input from the lattice that we used for chi2b and for entropy density at 0 mu, then this is the location that we obtain. We also obtain a covariance ellipse, again propagating lattice data. And this is contrasted here with this orange line is the estimate of the chemical freeze-out in heavy ion collisions. Different numbers here are energies in GeV. And of course, you would not expect critical point below the freeze-out if you trust the concept. If not, then everything is possible, of course. Comparison here with other estimates from the literature. We'll not go into detail, but there are estimates also based on lattice data, which look for these youngly edge singularities, so-called, which again connected to development of phenomenologic behavior of thermodynamic potential near phase transition. Then there are estimates from effective approaches, which all are well constrained at 0 μb with lattice. And there are a couple of studies which use heavy ion data, actually, not in the way I'm going to discuss, but in a different way using finite size scaling. There are also estimates of T and U. So I would say that as far as other theoretical approaches go, we are in the similar ballpark, or they are in the similar ballpark as we are.
So how are the errors calculated in the MUB?
The errors in this ellipse? Or
in the MUB value that you put?
This one. Yeah, so okay, so essentially our input is this Chi2b and S prime T. These are entropy density and baryon susceptibility at 0 chemical potential. And if you take it from lattice, it usually comes with error bars. So we just propagate those lattice error bars. And that's how we got the errors. Well, we got the full covariance.
So you were starting with this lattice, which is at UB equals 0.
Exactly. Mm-hmm.
And extrapolating to UB of 600 MeV.
Yes.
That seems like a long extrapolation. And how much do you trust that, and how much do you trust that, the leading order works over that long a distance?
So I don't know yet how much it runs. So this is resulted mu square order as it is, and how much it may change or not is under investigation. What only thing I can say is that where we have lattice data, we seem to the next to leading order coefficients seem to be consistent with 0. But of course, if you multiply it by maybe to the 4, the error may well blow up. So I don't have the answer of how much one can trust it at the moment.
Can I ask a question?
Yeah.
So how do you get those points for different beam energies in that plot?
Oh, this? Yeah, so this is from a parametrization of chemical freeze-out curve. So there is B versus square root of S parameterization. So these are fits to yields, hadron yields at different energies. And then
there's no fit for such low beam energies, right?
Oh, there are some at 3 GeV and also from AGS and from Hades. There are some data points. They are not as good as higher energy data points, but there is some also at lower energies. Okay, so just an aside. So there is also a development which we did with Wuppertal Budapest collaboration, which actually looked at this extrapolation of constant entropy contours from imaginary mu for case of strangeness neutral equation of state. So this one is not strangeness neutral, it's mu s equals 0. And this one is strangeness neutral, which means non-zero strangeness chemical potential. And so there, a more rigorous statement which we were able to obtain is to exclude critical point that may be less than 450 MeV on a 2 sigma level. So 2 sigma, one-sided 2 sigma, so that means 98% confidence interval or so, that there is no critical point below 450 MeV. Okay, so this is, so question is still open. I think we are making progress. We are able to say that we exclude critical point below 450 MeV rather than disfavor it, as we said before. Because disfavor, what does it mean disfavor, right? So here we have something which is on a 2 sigma level is not there. And we have some indications, not only from this work, but also from other works in the literature, that if there is something, it may well be roughly in this area, and potentially close to the chemical freeze-out line at square root of S, roughly 3.5, maybe to 5 GeV.
Sorry, I have to say, I missed your distinction between exclude and disfavor. Can you give that again?
So this is excluded on a 2 sigma level. That means so here.
So at some confidence, at some 90% confidence level or 95% confidence level.
95 one-sided, so it's actually 98.
98% confidence.
Yeah.
Okay, excluded at some confidence.
Yeah.
Good, okay. So I guess this doesn't contradict STAR's measurements, but some point it would be good to put these calculations and experimental determinations on the same slide.
Yeah, that's
right.
Coming.
Okay, good.
Let's see. Yeah, I think we'll have enough time. Okay, so no, wait. Okay, so what I wanted I'm actually getting there because you can see that it's fairly close to chemical freeze-out, these predictions, and
So
that
this
makes
black line
sense.
is the first order transition line?
The black line is the first order phase transition line. So
by hand or something?
by Maxwell construction.
Okay.
Yeah. Again, through using these contours that we obtained. Yeah, so that is also estimate of the first order line, but yeah, the main point here is that it is consistent with being close to freeze out in heavy-ion collisions, and so the natural question is whether we can, and of course we've been doing this for a long time, whether we can find something with heavy-ion collisions. And so that brings me to this part about event-by-event fluctuations, which we usually use in heavy-ion collisions to look for critical point. There are different ways of looking at it, why fluctuations should be sensitive to critical point. One way to look at it is to consider equilibrium statistical mechanics. You will observe that derivatives of the grand partition function are nothing else but cumulants of for instance, baryon number distribution. In grand canonical ensemble, in equilibrium, of course, but nevertheless, theoretically, high order derivatives, and then critical point is a singularity, so you expect these things to be sensitive to critical point, and utilizing even some more model-independent considerations related to universality of critical behavior, one can also look into behavior of the correlation lengths near critical point, and cumulants of higher and higher order are proportional to increasing powers of correlation lengths. So, of course, this has been one of the primary motivations in beam energy scan, to look for some non-monotonicities, maybe of the proton cumulants, and then trying to interpret that as being due to critical point. There are other uses of cumulants. In the later part of my talk, I have this one, which I hope I will get to, and also things like speed of sound and the like balance functions, balancing between charges due to conservation laws can also be observed, analyzed with cumulants. But focusing on critical point, so this is an illustration how in equilibrium cumulants would be nice probes. Why? So this is phase diagram of actually nuclear matter, nuclear liquid gas transition. So it was questioned which temperature it is. So it's shown here, around 20 MeV nuclear liquid gas. So this is, of course, density, which jumps from dilute to dense matter. That's all known for any liquid gas transition very well, but I'm also showing here scaled variance, skewness, and kurtosis, so second, third, and fourth order cumulant ratios. And you see that as you go to higher and higher order, we get higher and higher sensitivity of the cumulants to critical point. And this is also illustrated in the phenomenon of critical opalescence, again, in equilibrium and for very large number of microscopic degrees of freedom. Once you reach the close to critical point, large density fluctuations make the fluid opaque with regards to, for instance, shooting lasers.
For this liquid gas transition, this is a dynamical system or not?
No, this is just thermodynamics. So this is equilibrium calculation. Yeah. And here is a dynamical calculation. And it's another example for a microscopic simulations. a little bit closer maybe to experimental reality, because we don't, in experiment, we don't deal with just formulas, but we deal with particles, with finite number of particles. So the illustration here is the simulation of a Lennard-Jones fluid. So again, liquid-gas transition, which is known to be in the same 3D using universality class as QCD. And this is simulation near critical point of that transition. So this is just brute force molecular dynamics. So all pair interactions near critical point, and you can then look into subspace of the system, how many particles are in different snapshots and what is the distribution. So you will see that as you increase the size of the system, you get this omega. Omega is the scale variance with some correction for total number conservation. And you can see that there is a large signal as advertised in principle if you do everything in coordinate space. Furthermore, you can look also in the same setup at high order cumulants, Qness and kurtosis. So here we take 400 nucleons in a box, because we only have 400, especially at low energies where there is no baryon-antibaryon production. And so even for 400, one can see, so this is dependence. Let me just focus on this one. Kurtosis as function of alpha. So alpha means what is the fraction of the total volume we are covering by our acceptance, right? For instance, rapidity cut in heavy ion collisions would be an equivalent here, roughly speaking. And so we can see numbers which are actually significantly negative. So you see here -5, and you see here -18 even. This simulation very close to critical point. Again, we let it equilibrate, so it's still idealized case. Nevertheless, we have very much finite particle number statistics. And
This is in a box, not expansion.
yeah, it is also in a box, not in expansion. Nevertheless, even for this very finite system, we can still see this singular behavior or its remnants, which are not totally washed away. We also studied more things. We actually studied also expansion dynamics in this setup. It still requires more work to make it more realistic. But here I'm only showing another interesting result we obtained, the question of equilibration, right? Because there is this critical slowing down, and in particular, maybe there is just no time to equilibrate at all in heavy ion collisions. And maybe there isn't time to equilibrate completely, but what we observe is that non-Gaussian cumulants equilibrate about as fast as for instance, second order cumulant. So at least going to high order doesn't kill this finite critical slowing down related limitations that we have. Well, at least in this approach. Okay, so these were sort of examples and motivations that cumulants are sensitive, and even in a finite system. Nevertheless, there are still significant differences between theory and experiment. We have not coordinate space, but momentum space where measurements are performed. We don't have a heat bath. We have a vacuum, expansion in vacuum. We are dealing with numbers which are not exactly conserved usually, such as protons rather than baryons. And the question of volume is not really well defined even in heavy ion collisions, and other things. So dynamical descriptions are needed, and quantitative calculations of critical signatures are in progress. There have been quantitative calculations of non-critical signatures. So so now to shift this discussion to BES-II data, I'm showing us plots, I think, from Nushu. So these are the data from BES-II for second, third, and fourth order cumulants. These are net proton cumulant ratio. These are also factorial cumulants of protons and antiprotons. And so what you can see here, some structures which I will get in a moment. But what you can see here is that mainly there is this curve, dashed blue curve, which seems to describe the data mostly above, say, 20 GeV square root of S. And this curve is hydro EV, hydro excluded volume. So what is it exactly? So hydro excluded volume is a calculation of non-critical expectation for proton number cumulants in heavy collisions at BES energies, which we did a couple of years before. So it was a prediction with regards to BES-II data, where we used we used music simulation of hydro 3+1D, and the new ingredients were done at particularization. So when we transform the fluid into hadrons, we implement effects of exact global baryon conservation. So what is exact global baryon conservation? So if you have 400 baryons in the beginning, you will have 400 net baryons at the end, in the full space. And so that is one effect. The second effect is repulsion. So repulsion among baryons. So you don't allow two baryons to overlap in space. So that's what excluded volume models. And there is an additional parameter involved. So to not have freedom there, we fix this parameter such that corresponding hadron gas with excluded volume repulsion is in line with latest QCD data at 0. So to summarize, we included baryon conservation and repulsion. And since it's a fully dynamical calculation, we also did kinematical cuts as an experiment. We have not incorporated here critical point dynamics. This is not critical hydro, so that is consistent. Additional local conservations between these baryons or volume fluctuation. A hadronic phase we looked briefly, but also in the plots shown here, it's not included.
So what is the local conservation?
So local, because of baryon conservation, if you produce, for instance, BB bar pair, right? So these produced baryons have to be balanced by antibaryons somewhere in the fireball, right? So if you do global, it means it can be balanced anywhere in the fireball, no matter how far apart it can be. So you could balance baryon at forward rapidity with antibaryon at backward rapidity. Local is a more strong constraint. You want antibaryon to not be too far away, right? Because you have to consider causality as well. So that would be a more stringent.
I see that it's applied at some of the least energies, right?
Yeah, at the least energy we applied it. At RHIC we did not yet apply it really.
And the choice is really how do you make that choice?
There is so it needs constraints. Yeah. Let me again.
What was the initial bound number?
Our initial baryon number is so what you conserve is the total baryon number integrated over hypersurface.
Yes.
Yeah, so it's number of participants. You want so when you create baryons, antibaryons, mesons, everything else, and you calculate B minus B bar, you want that to be exactly equal to the number of baryons if you integrate hypersurface. Yeah, and not on average, but exactly, right, in each event. Okay, so this is another look at BES-II data, same data, just different plot. And so if you look into more details, you will see again the description of the data above 20 GeV by non-critical hydro. There is maybe some dip in kurtosis. Personally, I'm not sure about it because this dip should also show up in factorial cumulants, but it seems to be a combination of various 2, 3, and 4 particle correlations. And if I look, for instance, at kappa 4 is a 4-particle correlation. There seems to be some indication for a dip, but the error is too large. But what is interesting here is that if you look at factorial cumulants rather than on proton-cumulant ratio, you can clearly see some changes of trends. So here kappa 2, which was decreasing, now suddenly goes up, seems to want to go up as we decrease the energy. And kappa 3 over kappa 2, so third-order factorial cumulant, shows the peak. If we don't even look at the model, but just at the data. So more structures here in factorial cumulants. So I think this is our first conclusion from BES-II data. That there are ordinary cumulants, which we talked about a lot previously. They are good. There's nothing wrong with them, especially at high energies where maybe you want to connect to conserve density, right? Their ordinary cumulants make a lot of sense. But when we go here to critical phenomena at high mu B, factorial cumulants seem to show some more interesting
ask a-
behavior. Yeah.
A question about the experiment, since we have an expert in the room. So on the middle panel, can you give us a very brief description of the error bars, and are they correlated, energy to energy?
So the bars that you see are there statistical.
So the long bars are statistical?
Yeah.
So
And
these
the
are
shape bands are-
independent bunch of points.
Yeah, the long bars, okay.
So the systematic is smaller, but
Yeah.
so even if we're correlated, then your ability to kind of move in a coherent way is.
Mm.
But okay, well then statistically, how, for instance, the lowest panel, since it's statistical, how significant is that rise?
Which one? In the lowest panel?
So if it's statistical,
It's all zero.
It's consistent with zero.
I would
And
say
last
it's
two,
consistent.
I mean, last 2 points are pretty,
The lower panel?
This
lower
two-
middle panel, yeah,
Lower.
okay.
To me, it looks like zero at the moment. At the moment, who knows? Maybe something will burn out if
Why?
there is a possibility to decrease it. Yeah.
Why your model line doesn't have uncertainty?
By model what?
Model line doesn't have the uncertainty.
Yeah, why a model doesn't have uncertainty.
Oh, okay. Because it's a model.
Theorist makes mistakes, not errors.
Okay, it's a calculation for a particular
Oh, there is
set of
of course
parameters.
uncertainty.
There is uncertainty, but some of the input
Not
you
for
use.
us.
Yeah, I mean, some of the input is kind of difficult for us to propagate. It comes from elsewhere, and I guess we could do something here, but then we would probably overemphasize uncertainty of just one parameter of the
But you
model.
have statistics on that. You do Monte Carlo sample.
No, yeah, we also did Monte Carlo sampling to validate, but the lines here are analytical. Yeah. Okay, so what is factorial cumulants then? So, and why are they so much more interesting potentially? So factorial cumulants are these called also irreducible and particle correlations or integrated correlation functions. So essentially, this is another way to look at a distribution. There is one-to-one correspondence between ordinary cumulants and factorial cumulants. Factorial cumulants have the advantage that they subtract low-order correlations when you go to the next order. So for example, C2 hat, second order subtracts the self-correlation here, C1. So you probe two particle correlations only and not self-correlations. And then when you go to third order, you subtract both self-correlation and also the two particle correlations, which you already determined before. And so, and if one looks at various physical effects, there are some estimations indicating that some non-critical effects like baryon conservation exuded volume are small contributions in high-order factorial cumulants. On the other hand, critical point leads to singular behavior, which is as singular as in ordinary cumulants, because the singular behavior is always in the leading order multi-particle correlation. Okay, so then let's be here optimistic now and then say that deviations from baseline that we see are because of critical point. So if this is the case, what we could potentially conclude, so to set the stage, I'm borrowing a slide from Misha here, where he drew possible qualitative behavior of factorial cumulants. And so normally you would see some purely due to critical behavior, some peak in omega-2, maybe non-monotonic behavior on omega-3 and also omega-4. For omega-2, clearly there is a baseline, so you have to subtract the baseline. And if you subtract the baseline, the indication would seem from the data that maybe this turn at low energies could indicate approaching critical point. However, if we subtract baseline from omega-2, from second factorial cumulant, we should be also doing the same for other factorial cumulants. And so we see that this right side of the peak in the data for kappa 3 over kappa 1 is described by non-critical baseline. And if we subtract the baseline, we actually see that this difference between measurement and baseline is 0, and then it becomes negative. So at low energies, it is negative deviation. So I guess the conclusion that controlling the non-critical baseline here is essential. And if I allow myself to again entertain the possibility that the deviations are because of critical point, what I can do, I could say, okay, I have positive deviation for C2, negative for C3, so I'm gonna now exclude this negative C2, positive C3 from the phase diagram near a critical point. And if I exclude these regions, I'm left with this band here, which is a region, allowed region to coming from BES-II data, just qualitatively to have the correct signs of second and third order factorial cumulants. So
this red block is within your band, right?
What red block?
The red area to the right of on top of the critical point. This thing is still in the band, right?
This is still in the band.
So, and this is also above the freeze out. So there is some sensible place which could survive, right?
Yeah, seems so. And
This is statical model calculation.
Huh?
This is a statical model calculation.
sure.
Yeah, sure. So that's why we look only. I dare only look at signs and not more than that here.
Maybe even a sign will wash out.
Yeah. So actually, we have some here observation that the allowed region is here, but the freeze out line is below it, right? So it seems that freeze out of fluctuations may be happening not where the freeze out of the yields is, if again we follow this interpretation. And in principle, there is nothing fundamentally wrong with it because there is non-equilibrium dynamics and there are memory effects associated with fluctuations, more so than with the yields. So this qualitatively also has been known, that you can have this negative skewness in this case, also there where in equilibrium it would be positive. But of course, more has to be done. Okay, then for the going to lower energies, I will just point out briefly that, again, liquid gas transition, which I already mentioned. So it may not only be a toy model for phase transition, it may actually be relevant in combination with the QCD critical point, especially when you go here to lower energies from RHIC fixed target. So it's a model calculation, again, of how kurtosis from liquid gas transition actually shows remnants also at higher temperatures, and essentially any model calculation you may take which has liquid gas shows the same result. So I think this will be increasingly relevant as we go to lower energies probed by RHIC's fixed target. Okay, now I want to briefly mention some another way to look at factorial cumulants and also some maybe a wish list for start of what we also want to see from experiment. So another way is the so-called, which we call here stack ratios. So you take factorial cumulant of given order and you divide it by the mean to the corresponding power. And why it is nice, because you can show that this ratio is not gonna be, it will be independent of acceptance if all correlations are long range. So if the source of correlations is global conservation plus volume fluctuation and plus possibly some efficiency corrections, which are, if it's uniform, one can even leave them as it is, then this quantity at a given energy will be constant. So you increase rapidity window and the quantity should stay constant if there is only long-range correlations. And moreover, one can also show that protons and antiprotons should be the same. So there should be k equal to here at second order. And we could only look at BES-II at the moment.
BES-I.
Yeah, exactly, BES-I. We would like to look at BES-II, but at the moment we only look at BES-I data. So we see that maybe there is, the scaling holds approximately, but maybe there are other details involved. What we see is that there is a strong separation for a second order stack ratio of proton and antiproton in the data. So there is almost factor 2 difference, for example, 27 GeV energy. And these two solid lines, which are almost on top of each other, is what we get in hydro calculation. So hydro, single fireball, essentially predicts no splitting. Data show huge splitting between proton and antiproton. And
if I look carefully, hydrogen is still lower of those. The black lines are lower than the blue.
Yeah, slightly lower.
The trend is there. I mean, it's the
Yeah,
magnitude
but
of course.
it's a huge effect compared to nothing,
No,
right?
I agree. Just
So you should compare solid lines because dashed line is a different
Very
model.
black line.
There's a black line on
There is black line on top of blue line, just a little bit below.
the fact that you don't see.
So this is the difference in model, and this is the difference in experiment. So this doesn't work, and so we have to come up with something else. So what we entertained here is that instead of single fireball, we have two fireballs, namely produced and stopped matter, which don't talk to each other. So this is the extreme assumption. So produced matter is essentially proton-antiproton pairs for this measurement, and stopped protons are protons from the nuclei, which end up in the acceptance due to stopping. So if you make this extreme assumption, now these two lines is now new model prediction of two components. And well, actually we basically overpredict things here. Splitting is too large compared to data now, apart from maybe some of the higher energies. And this is just as function of collision energy for largest acceptance. We just take difference between proton and antiproton. So data is here. This dashed line is our hydro, so 0 by almost 0. And black line is two components. So seems that single fireball doesn't get the job done. Two fireball which don't talk to each other overdo it. And perhaps we are somewhere in the middle. So some opportunities for BES-II is to look at this acceptance dependence. So we're not only interested in energy dependence, we also want to look at rapidity cut dependence at fixed at each energy separately. And then see if it's first of all, if it's flat or not, because if you also look at some predictions from theory, is that the scaling should be broken by critical points in higher cumulants. But also, of course, we want to see how much of this effect is there. Presumably, the splitting is still there. The error bars are pretty small here already in BES-II. But then looking at high order cumulants is a new possibility. And well, it's still in the works, but covariance of proton and antiproton can also be used to probe baryon annihilations. There are some early indications that we see. So this observable, I think, which was not explicitly published in BES-I, I would like to see in BES-II. Okay, so I just maybe have a couple of minutes here on the last topic, which is now not RHIC, so it's a change of gear here, but it's actually kind of a revival of an old topic. I think also RHIC has been involved in the measurements in the early days. So the idea is whether we can have this QGP signature of QGP. Of course, we had a lot of them in the field, but particularly in fluctuations. Why? Because in QGP, degrees of freedoms are quarks, which carry fractional charge, while hadrons carry integer charge. And if you consider fluctuations of a number carried by carriers which have smaller units, such as quark compared to large units, fluctuations will be smaller. So this is, of course, the old idea, and the D measure has been introduced long time ago, in the grand canonical ensemble. If we throw away all other effects, we would see a large, more than factor 2 difference between these two scenarios. And however, no quantitative calculations have been done for QGP. Okay, this is an illustration of that. Actually, it's been already 25 years.
So if you go back to that cartoon,
Yeah.
I understand the basic assumption. I mean, there's, quarks
This
eventually, turn into hadrons.
Yeah,
And it's a complicated magic. And how do you neutralize color charge?
Mm-hmm.
And there must be correlations in that process.
Yes.
Which will mess up this simple, counting of basic constituents.
Yeah, the counting is so how we normalize these fluctuations, right? Charge multiplicity.
Well, I think there's a kind of an unknown dynamic in it, and how you neutralize color charge.
Yeah. So we know that we will conserve charge no matter what. So that's one assumption.
That's what I agree on.
And second assumption, okay, so I'm getting there. I just want to point out that actually this is also why we're doing here, because we do it a bit more quantitatively than before. So there have been theoretical prediction, there have been measurements, which, as you can see, kind of die out a little bit over time. The interest seems to be getting lost. So why are we doing it here now? So this, actually, this was our attempt before to do it with hadrons only, and we mostly fail. So the difference between hadrons and quarks comes at hadronization. At hadronization, we have omega is net charge fluctuation divided by number of charged hadrons. And the question is how we convert quarks into charged hadrons, right? Okay, so the usual argument, and I think I have it on the next slide, is conservation of entropy. So I'm gonna just mention here that, okay, so what we do here is that we not only stop at hadronization as before, we also incorporate correlations in hadronic phase, which because of resonance decays. We incorporate local charge conservation because we want to see whether it's QGP or it's some local dynamics which have nothing to do with QGP, just that T-bar pairs don't go too far away. And then kinematical cuts as in experiment. So, okay, so this is how the conversion takes place. So we have this observable at hadronization, charge variance divided by charge multiplicity. If we have hadrons, it's clear, right? So we have hadrons for both. This is already hadrons, and this we calculate using hadrons. And it is basically 1 with some corrections. Like Bose statistics could make it more than 1. But for hadron gas, this is 1, approximately. For QGP, it is not clear how to calculate this quantity because we have quarks, but this is not what we have in experiment, right? In experiment, we have charges. So what one can do here is to make a series of transformations. So we can divide and multiply it by entropy, and then we can introduce entropy density, and then this whole quantity split into 3 parts. One is charge susceptibility over entropy density. So this is property of equation of state. So here there is no problem with QGP. Second term is entropy per charged multiplicity. And so this has been estimated independently of this assumption. So this doesn't involve fluctuations. So it doesn't matter what we assume for fluctuations for S over N charge. What matters is just the final number. And the third factor is the fact that when neutral resonance decays into pair of charged particles, it increases final charge multiplicity. So this is again estimated using thermal model because it has nothing to do with fluctuations. So this is the way how we get around this hadronization problem. Maybe there are better ways, but it also seems to make sense if we do calculation using lattice equation of state. So at high temperatures, it approaches 300 UGP limit. Around transition temperature to HRG, this quantity is consistent with 1 as we expect. And then any value in between would be the value of omega as if we assume that fluctuations froze out at that temperature. So extreme case QGP, other extreme hadron gas, and then there is anything in between. Okay, so I'm gonna skip these details. I will just mention that we can use some basic considerations like charge conservation to implement resonance decays. They reshuffle balance between self-correlations and two-particle correlations. Again, these are details. For local charge conservation, there is a new formalism where you can put in by hand this correlation, not have it global, but also localized in space, where balancing charges how far they are separated. And then for kinematical cuts, we need this acceptance probability, which we can also get from blast wave model. These parameterizations are well known. So then if we put everything together, we have this result, which for the D measure, where several inputs. So the main input of interest is omega. It defines fluctuation, normalized fluctuations at hadronization. One for hadron gas, and we estimated as 0.36 for QGP, so almost factor 3 difference. And then after hadronization, resonance decays change things a little bit. Then local conservation is also there because total charge doesn't fluctuate and balancing charges are not necessarily far apart. So there is additional parameter here. And then momentum cuts. So we calculate fluctuations not in some abstract integrated over momentum space, but exactly as it's measured in experiment. Okay, so if we compare this to data from LHC run 1, and blue lines is hadron gas scenario, red lines is QGP scenario, and different style of lines correspond to different assumptions regarding this charge conservation. So what we observe is that hadron gas can only reasonably describe data if we assume a very local conservation of electric charge. So we have to have these two charges produced which cannot go apart too far. So if you fine-tune this parameter, we can describe data with hadron gas. For QGP, we actually can describe data almost with any range of charge conservation. And so it's a much lower sensitivity. One can see why in this equation, because omega of QGP is much smaller than hadron gas. So there is much less variation because of local charge conservation. So this is one observation. More seriously, we are considering Bayesian analysis because we have two parameters. We have omega, hadron gas QGP, or something in between, and we don't really know what is the range of local charge conservation. So we can also treat it as a free parameter. And if we do it in the way it is usually done in Bayesian analysis, we assume uniform prior for simplicity, as they say, then we get this posterior distribution of omega, which seems to clearly prefer QGP. Maybe more quantitatively biased factor analysis rather would say it's a moderate preference for QGP. We can also consider something more sophisticated, and we can say, okay, let's say that there is a preference for local conservation because balance functions show us that there is more locality than one would naively expect. And so if we assume that prior for local conservation is already localized, we can get a much more broader posterior for omega. Bias factor still gives moderate evidence according to this Jeffrey's classification, I believe it's called. But there is more work to be done. So sensitivity to assume prior is there, and it is currently under investigation. Preliminarily, we see moderate evidence for result of charge fluctuations in QGP.
This base effect is not so large. Still.
Well, yeah. So between 3 and 10 is moderate evidence.
Yeah.
So it's not so large. Yeah. Actually, what's nice is that Alice will come with new data from run 2. And I didn't talk about this in detail, but they made corrections which increased error bar, 2 different corrections for charge conservation. We are comparing apples to apples, but the error bar could be much smaller if one doesn't do these corrections, which we don't need in our approach. So we expect to have much more constraining power. Yes?
That's a question on the previous slide.
Okay.
How do we understand the scale of local charge conservation?
Scale?
Right. I mean,
Okay.
the sigma, how do you?
Yeah. I have, I think in backup slide, an illustration of this, which would be easier. Okay. Yeah. So this. So imagine this as rapidity or space-time rapidity. So essentially, if you have one charge here, what is the probability that that the balancing charge would be somewhere to the left or to the right? So this probability decreases with the Gaussian for local conservation. If there was global conservation, it would be just uniform distribution up to maximum rapidity. So the width of the Gaussian determines how far apart can the balancing charge be.
What caused this width, or what changed this width? Is it like hadronic.
Well, it depends on the production and transport of charge. And that we don't try to constrain here.
We should explain all the charge particle variables, right?
Huh?
This parameter should be explaining all these charge particle at the least measures in principle.
In principle, yes. And these other measurements, which are maybe not so sensitive to equation of state, can be used to constrain it potentially. So actually, the reason why I choose here this number is because I would get this number for baryon conservation if I analyze proton cumulants at least. So I just say for simplicity, let's assume it's the same for charge.
But protons are heavier than baryons. So
Yeah, but this is in space-time rapidity.
Okay, fair enough.
It's not in kinematic. Okay, so I'm over time here. There were a bunch of topics. So this is my summary. There is some quantitative constraints on QCD, critical point exclusion, and some indications where it might be beyond that. For BES-II data, we have non-critical physics describing proton cumulants above 20 GeV, deviations from the baseline at below 10 GeV, roughly, which may indicate result of fluctuations on the QGP side of the crossover if we attribute these deviations to critical behavior. There is antiproton puzzle, so huge difference between protons and antiprotons, which we cannot describe in the standard scenario of single fluid hydro. And net charge fluctuations at LHC are revisited and show moderate evidence for that the result of those fluctuations happens in QGP. So improved description of baseline will be important to draw more conclusions from BES-II data. And acceptance dependence of factorial cumulant is another possibility in addition to beam energy dependence, which will also hopefully help us understand antiprotons better. Thank you.
Thank you very much. More questions? Yes, Spencer?
So you are talking of doing calculations with baryon, but basically the data is protons and antiprotons.
Yeah.
What about the other baryon? I mean, how do you account for fluctuations between baryon flavor, either random or because of phase space limits or
Actually,
exclusion principle or things like that?
Okay, so actually the calculations here in hydro are for protons. Where is my hydro slide? It is for protons. So it is for protons, and we compare it with protons. We use hadron resonance gas model in this globally canonical ensemble, and our interactions that we put in are flavor blind. That's how we treat them at the moment. But we take into account that we are not comparing all baryons, we are comparing subset of baryons to the data.
Did you include things like, baryon repulsions or attractions at low?
I include repulsion only here.
But it could very well be the deviation might be
from attraction.
From attraction.
Right. We know the deuteron is bound.
And you would think that at lower density energies, the attraction slowly comes in, right? So I mean, but that's speculation.
Yes. I just have a naive question on the same slide actually. So why is this should be hydro? I mean, like you said, well, you have this the program, for example, like local motivations and so on, and then if you use the transport, and then you wouldn't have that. Right?
Yeah.
And then like you have this nice simulation with the molecular dynamics and stuff. Like I just.
Molecular dynamics are not really on the level of quantitative description, at least the one we used. We only have just particles there, not hadron gas or anything like that. So hydro, because it's it is a standard model for at least higher energies, and the single particle spectra have been tuned. So what we do doesn't change single particle spectra, but it provides us realistic background to calculate these contributions to fluctuations. And so that is why we used hydro. I also agree that at lower energies, probably we want to switch to something less locally equilibrated than hydro. But the reason why we did it, hydro is there, and we go essentially from high energies to low. So it will seem like a natural thing to do.
So in this, and another question about this. So what kind of, so for the diffusion of the charges, what kind of like, well, for example, like what do you have?
Okay, so we don't actually have diffusion, right?
Okay.
So what we have is just canonical ensemble at the end of the evolution.
Yeah, because this is one other problem of the
Yes, so if we did diffusion, we would probably get something like local conservation, which I put in by hand in another part of my talk. But normally what local conservation does is stronger suppression from conservation law, so this blue line would go down if we had something like diffusion. That's my expectation, at least. And since we already below the data, there was not much sense to try to explain the data with or also technically it's not so easy to do. So if there is local, probably there is local, this deviation will be even higher here. That's my expectation at least.
Just to add, but then you should see it in the stack ratios, right? If you have low.
Yes, and we will see it in the stack ratios. So yeah, I would expect that, well, maybe not this slide. So yeah, if there is local conservation, I would expect this to also go down, but I don't know by how much a priori. Yeah.
And this new calculation of mu b, 600 and some.
Yeah.
So this is beyond the reach of star, I guess.
It is beyond B-manager's count.
Yeah. So where can one possibly measure it?
CBM?
Yeah, okay, CBM could measure it, maybe from fixed target could approach it from other side a little bit. But even here, I mean, it's not quite there, and there is of course an error bar here, but the signals, the crossover signal, it could very much be already in the crossover region. So it doesn't mean we shouldn't see anything.
You had,
Please.
yeah, you had an impressive number of significant figures on your, like 4 significant figures on your summary slide.
Did I have?
Probably want to back off on that.
Okay, for this.
The error bar.
Yeah, okay.
Summary.
Yeah. Well, you mean this one? Okay.
602.1 plus or minus 62.1.
Yeah. Okay. So this is propagating the errors
Probably
as it
too
is.
many significant figures.
Yeah.
It's fine.
Nancy?
Well, yeah, sure.
So if we want to go to higher chemical potential to reach that critical region, and then you need to lower the beam energy, right?
Yeah.
What if you will not be able to produce QGP at even lower beam energies? I mean, system does not cross the phase-out line. Do you think?
What does it cross the freeze-out line?
I mean, the initial temperature, for example, at the lower beam energies will be even lower.
Yeah. So
then you will not be able to produce the combined system.
Well, I mean, there are, I guess, 2 ways to approach the problem. One is that you calculate non-critical baseline as it is, and then you try to interpret without assuming you are in QGP necessarily. And well, second, I mean, well, it depends how you model things, right? It's not it's the question of the model, right? So because in the model you know if you're in QGP or not roughly, right? So if you don't approach QGP, you will predict that I don't approach QGP, and I can predict this behavior, which may be not related to QGP. And so can we understand the data with that? If the question is whether we can answer whether we reach QGP or not, well, maybe only indirectly, right? If we see indications for critical behavior, we could say that we must reach some QGP.
All right. I don't see any further questions, so let's thank you. Good end of recording.